Hi, everybody. So I'm giving this a shot. It's a new way I'm doing notes, so let's see how this goes. Hopefully it won't break it into parts by doing it this way, so just kind of bear with me as we go through this. So what we're going to be dealing with today is we're going to start with diluting solutions. So yesterday, last class, we talked about molarity of solutions. So our molarity was moles over liters. Or we could have done given mass over GFM times liters, same thing. All right, so this still holds true when we're doing a dilution. So when we do a dilution, we're going to take a concentrated solution. We're going to add water and decrease the concentration. In other words, we're diluting it. Diluting it. So we're adding water, so we're not changing the number of moles of solute in that solution. So we do not change the number of moles of solute dissolved in the solution. So we know that molarity equals moles of solute over liters of solution. Now the variable that we use for moles is always N. Liters is L. Right, so I can rearrange this equation so moles, or N, equals molarity times liters of solution. Now, when we're doing a dilution, we just said the number of moles of solute is constant. So we can say this: N is equal to the initial molarity times my initial volume. N is also equal to my final molarity times my final volume. And there's some math property here that says if this equals this and this equals that, that means these two things have to be equal. So we get molarity initial times volume initial is going to equal the molarity of the final times the volume of the final. And this is our dilution equation. So let's go ahead and do a problem. A stock solution of 18.0 molar HCl is given. How many milliliters of the stock solution are required to make 0.450 liters of a 3.00 molar HCl solution. Now, this is exactly what I do in the prep room when I'm getting ready to make you guys your HCl, your hydrochloric acid. And we use 3 molar all the time. If I ever gave you an 18 molar hydrochloric acid solution, yeah, I would lose my job because this is some pretty nasty stuff. Right? So we have to dilute it down to a form where it's really not going to hurt you very much. So we just do this quick calculation. Our initial molarity times our initial volume is equal to our final molarity times our final volume. Well, we're starting with an 18 molar solution. I want to know how much I initially need. My final molarity is going to be 3.00 molar. And my final volume is 0.450 liters. And when I do this math, my initial volume is 0.0750 liters, which is 75.0 milliliters. Right, so this is just a typical dilution problem, right? Not too bad. And you'll see some of these. Now, what we need to get into next, now that we've talked a little bit about molarity and concentration, and we talked about some of the solubility rules, right? We need to expand on some of those different things, okay? And what we're going to do is we're going to talk about electrolytes versus non-electrolytes. So if something is an electrolyte, it's a substance that can conduct electricity. Now, there are 2 ways the substance can conduct electricity. First way is if we have free moving electrons. And this is why metals conduct electricity. Remember in metals, the metallic bonds are that sea of mobile electrons. So we have all these electrons that can move freely throughout the structure. All right, those mobile electrons are what allow metals to conduct electricity. Now, there's a second way that we can conduct electricity, and that's having free moving ions. Free moving ions. Right? Now, a substance can have ions, but those ions can't move. Okay, so that's, for example, that would be our salts, right, when they're in solid form. So the salts are ionic compounds. They have ions, but in those cases, they can't move, right? So those won't conduct electricity. But if we can get those ions so that they can move, that substance will conduct electricity. Okay, so to conduct, you have to have one or the other of these, right? You have to have one of them. Now, let's talk about ionics first. Remember, these are our salts. So let's say, let's make this simple. Okay, we'll use table salt, NaCl. In solid form, it has ions. Okay, remember, its diagram would be this. So there are ions, okay, but in solid form, we have all these electrostatic attractive forces that are holding those ions in place. So solid salt is a non-electrolyte. It's a non-electrolyte. Okay, solid salts will not conduct electricity. All right, well, what if we take this solid salt, we heat it up, and we melt it? Well, it still have ions. But now what's happened? Well, remember, in that liquid form, this geometric pattern starts to break down. And as it starts to break down, these can start to move a little bit. If we have ions that can move, it will conduct electricity. So those ions can move, okay, so it will conduct. So if we melt salts, and it's not just NaCl, it's any of these ionic compounds, if we melt it into liquid form, it will conduct electricity. How about gases? Yes, we can make NaCl a gas. Okay, we just heated it up, but eventually it would boil off, and we would produce gaseous NaCl. So it still has ions. We know that these ions will be able to move like crazy. So again, if you have moving ions, it will conduct. How about if we take NaCl or any salt and we dissolve it in water and make it an aqueous? Well, it's a salt, so it still has ions. As soon as you put it in that solution, because of molecule ion attraction, this electrostatic attraction breaks down, and we get these individual ions in the solution that can move. So they can move still. Right? So they will conduct. So in solid form, they won't, because they can't move. Liquid form, they can move, so it will. Gas form, they can move, so it will. And in an aqueous form, it will. So these are our ionics. What about our moleculars? What about molecular compounds? These are our covalents. So like H2O, or an alcohol, any of our organics, CH3OH, okay, it's an alcohol, or glucose, C6H12O6, or ammonia, NH3. Okay, so these are all our molecular compounds and covalent compounds. All right. So does water conduct electricity? In any form. Well, remember, for this to conduct electricity, it's either going to have free moving electrons or have free moving ions. So if we look at the water molecule, right? These electrons are in this bond. They're stuck here. Okay, they can't move, right? They can't move between molecules, so the electrons can't move, right? This doesn't form ions either. Now, it does have slight charges. This side's slightly negative and this side's slightly positive, but those are not ions. So there are no ions, and there are no free moving electrons. Water will not conduct electricity. It is a non-electrolyte. It is a non-electrolyte. Now, I'm sure you guys are saying, hey, well, you know, if I go in my bathtub, right, I don't want to hold my hairdryer because I'm going to electrocute myself. It's not the water that's conducting the electricity in that case. So our tap water is not pure water. What's dissolved in our tap water? Well, there's chlorine and fluorine, okay, minerals that have charges. Okay, these ions, or these things that are in the tap water, are what are actually conducting the electricity, not the water itself. Okay. So when we look at these molecular compounds, they do not break into, okay, they'll dissolve, but they don't break down into different parts. Right? So we can have CH3OH aqueous. Okay. But this whole molecule stays together in the water. It does not break apart. Right? So in our water, this water molecule or this alcohol molecule stays together. Same thing with glucose, C6H12O6. It'll dissolve in water. Sugar dissolves in water, but it does not break apart. These do not form ions. They are non-electrolytes. These are all non-electrolytes. Let's try a couple. Let's say we have this, MgCl2, and it's in liquid form. Is that an electrolyte? Well, this is a salt, it's an ionic. So that means it has ions. Okay. It has ions because it's transferred electrons. The question is, can those ions move? And it's in liquid form, so this will conduct electricity. Sure. How about NH3 liquid? NH3, for those of you that don't know, is ammonia. Okay. Will ammonia conduct electricity? You know what? This is a bad example. We're going to come to ammonia later. Let's hold off on that one. I don't want to use that one yet. Sorry, my bad. Let's use CH4, methane. And let's say it's in gaseous form. So this is a molecular. Okay, so this means it has covalent bonds. It will not break apart. Okay, so there are no ions. Okay, this will not conduct. How about NaNO3 aqueous? Well, again, we know that this is an ionic. It will break into parts. It's going to break into Na pluses and NO3 minuses. So we have ions. They can move, so this will conduct. How about CaCO3 solid? This is another ionic. Okay. But in solid form, we have ions. They cannot move. So this will not conduct. All right, so hopefully you get a good understanding of what's going on here. Oop, my lights just went off. There we go. So there are actually different degrees of electrolytes. So we have strong electrolytes. Okay, those are the ones that we're going to talk about first. So when we're talking about stuff dissolving in water, electrolytes dissolve in water to produce various amounts of ions. Now, what do I mean by that? Well, some completely dissolve. Right? So, for example, NaCl, this is completely soluble. It will completely dissolve. But if we look at something like strontium hydroxide, hold on a second. Where's that? Let's not use strontium hydroxide. Let's use, how about beryllium hydroxide? If we look at beryllium hydroxide, this is an ionic. But it is insoluble by our rules. It will not dissolve in the water. So this doesn't produce ions. Yeah. It'll produce a few of them, but it's so insoluble that it really doesn't produce. So it does not conduct. So you need to look at your solubility rules here, right, that you made this week. Right? So you got to be careful with this. Now, the rule of thumb is this. The more ions produced in solution, the stronger the electrolyte. So some substances completely dissociate into cations and are anions. If they're going to completely dissociate, they're going to be what's called a strong electrolyte, because they're producing lots of ions. NaCl solid is a perfect example. When we put it in water, this completely breaks apart and we get all Na plus aqueous and Cl minus aqueous. Okay, so these are our strong electrolytes. Now, there are some electrolytes that only partially dissociate. So some electrolytes will dissolve in water, but only partially dissociate. So our molecular ones, our molecular formulas, they dissolve. But do not dissociate, which means they produce few or no ions. Which means they're weak electrolytes or non-electrolytes. So a perfect example of this, of what we're talking about here, are the organic acids. And we'll spend time in organic talking about organic acids, and when we do the acid-base unit, we'll spend a lot of time about talking about organic acids. But organic acids are weak electrolytes. They'll conduct electricity, but not very well. So acetic acid, CH3COOH. So this is acetic acid. It will dissociate. It will produce CH3COO minus and NH plus. It will dissociate and form these ions. But very little of it will do it. Okay. So if we look at this, when we put the acetic acid in water, it does produce this, but it only produces very few ions. It does produce ions in the solution, so it's going to conduct electricity. But since it produces so few ions, it's not going to conduct electricity well, which is why it's a weak electrolyte. So now the problem is we haven't gone through the acid-base unit. And you have to be able to identify whether a substance is a strong electrolyte or a weak electrolyte. So what we need to do is we need to talk a little bit about acids and bases so that you can predict whether or not the substance is a weak or strong electrolyte. So we're going to quickly do some stuff with acids and bases. Let's just say acids and bases quick. So there's some different types of ways that we define acids and bases. So you might remember Arrhenius. So Arrhenius defined an acid as anything that produces protons. Remember, a proton is really just an H plus ion in aqueous solutions. Example, HCl. If I put it in water, it will dissociate and we will get H plus aqueous and Cl minus aqueous. So this is an Arrhenius acid. It's producing H pluses. Arrhenius defined a base as anything that produces OH minus. Which is a hydroxide ion. In aqueous solutions. Example, if I take NaOH solid and I put it in water, it will dissolve and dissociate into Na plus aqueous and OH minus aqueous, which is making it a base. Now, there are actually two more types of acids and bases, and we need to talk about one of them right now, also called Bronsted-Lowry acids and bases. In Bronsted-Lowry, acids are defined as proton donors. They donate protons to other species. Okay, so, for example, we can define HCl using Bronsted-Lowry. If I take HCl and put it in water, what actually happens is this H right here is donated to the water molecule. And what we really get is H3O plus aqueous and Cl minus aqueous. This is what's called a hydronium ion. For our purposes for this class, or at least for right now, H3O plus is really equivalent to an H plus. They mean the same thing, all right? We're just defining the acid in a different way. So this way up here, we're producing this H plus in water, all right? What we're saying with Bronsted-Lowry is that H plus is still being produced, but it's being donated to the water molecule itself, so we get a hydronium ion. They mean the same thing for our purposes. It's an acid. Now, let's talk about Bronsted-Lowry bases. These are proton acceptors. And this is where I want to come back to ammonia, NH3. If I take NH3 and I put it in water, this is actually a base. And what happens is it takes one of these hydrogens from the water, okay, it accepts an H plus, it takes a proton, and it produces NH4 aqueous, plus one charge, and OH minus. Okay, so ammonia is a base, and in aqueous solutions, it will conduct electricity. Now, this is kind of overlapping the acid-base unit. I get it. We're not there yet. We're not ready for it. So that's why we're just kind of talking a little bit about some things. All right, so let's talk about strong and weak acids. Again, we're going to do a lot more with this. Okay, our big unit all on acids and bases. All right, so for now, you just need to know what are the strong acids, and if you know that, you're going to know how well they'll conduct electricity. So a strong acid completely dissociates. Remember, if it completely dissociates, it's a strong electrolyte. Strong electrolyte. Because it produces lots of ions. Now, you just have to memorize the strong acids. There's 7 of them. HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. There are 7 strong acids. Everything else is weak. All other acids are weak. In other words, they don't completely dissociate. Which means they're weak electrolytes. So there's tons and tons and tons and tons and tons and tons and tons of types of acids. If you just memorize the 7 strong ones, everything else would be a weak one. Okay, so now, HI. Okay, this is a strong electrolyte. Okay, it will completely dissociate. So if I put it in water, it will completely form H plus and I minus aqueous. It's strong. It's one of my strong acids. Well, let's take HNO2. HNO2 is not one of my strong acids. It's a weak acid. It will produce H plus and NO2 minus aqueous. But in reality, it doesn't produce many of these. Most of it stays over on this side. And this is all equilibrium stuff that we're dealing with, right? So this forms few ions, which makes it weak. Same thing for the bases. So our strong bases, these are going to completely dissociate. Again, they'll be strong electrolytes, lots of ions. Right? So I'm going to give you the strong bases. Again, you're going to memorize these. So for our strongs, lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Those are strong ones. Weak bases. Magnesium hydroxide. It'll form ions, but not many. Ammonia. Again, it will form ions, but not many. A fluorine ion is actually a weak base. The acetate ion is a weak base. And the ClO2 ion is also a weak base. Right? So these will conduct electricity, but not well, right? Because they'll only form a few ions. These guys, okay, they will completely dissociate and form lots of them. So remember, the more ions it produces, the stronger the electrolyte it is. Oops. All right, I think we're going to stop there. We'll pick up with titration on next class. All right, make sure you do the reading in the textbook for this. It will help you go through it again. And we will see you next time.